Thank you, Steve. Thank you.
Thank you. Thank you.
I don't even need, Dean needs to do an intro slide anymore. He just crushed it. um, but yeah, so our talk is going to be modern C++ inside of implants. And the code that you'll be seeing for our talk today comes from my course, the 670 course. It's going to be a sneak peek at a lab that we made in day 5, where you create a custom loader to load like a DLL manually, okay? And so please, if you could give me a show of hands, how many of you have some experience with C++? A few hands. Dang, raise your hand. It's like I'm C. Okay, cool. All right, so that's really awesome. Okay, for those that don't know C++ very well, all right, that's totally fine. Go ahead and take a power nap. I'll wake you up when we're done. But yeah, so you don't need the fear of the Reaper that is C++. Okay, so we'll hopefully shed some light about modern C++ and how you can use some of the things that C++ offers, some C++ paradigms and whatnot, to have a custom loader for like red team operations or red team engagements, stuff like that. Okay, so Steve already said everything about me, so I'll kick over to Kevin.
Yeah, Kevin Ott. I'm a red teamer at NVISO Security, where we do mostly Tiber engagements, red teaming, purple teaming, and also a lot of R&D to support our red teaming efforts. And as Steve already mentioned, I'm an instructor in development for the SUNS 670 class, which Jonathan has authored. Yeah, happy to be here, and let's get started, I guess.
Yeah, let's go ahead and crush it. All right, so modernizing the loader. Why do you want to do this? I think Mark was talking about C++. You know, I pity the person doing C++ or pity the person doing assembly, stuff like that. It's actually not too bad, right? There's a little bit of a learning curve jumping from C to C++, but it's not too bad. So some of the things that we're going to go over today: brace initialization, using standard vectors, standard strings, so you got like ASCII and WCHAR or like Unicode, UTF-16. Then we also have decltype and bitcast. So we'll go through these in just a little bit more detail. Kicking it off with brace initialization. This is kind of cool, and it's a nice way to go ahead and initialize some of the variables that you're creating throughout your program inside some of your functions. And for me personally, what I like to do is I like to initialize all of my variables right at the top of the function. I've seen so many code where people just initialize variables kind of like they do in Python: when you need it, where you need it, right? Don't do that. If I'm doing code review for you, I will smack you and say, nope, don't do this, put it at the top of the function. But in any case, a lot of times for red team operations or creating an implant or capability to be used for a red team operation, you will have to have some kind of communication to your C2 infrastructure. And so you could do that in a number of different ways. One of the ways is to create like a custom packet. A lot of times people use a structure, something like this, like a message. This is just a very, very contrived example of a structure that has two fields. One is a standard string for a username, and one can be like an unsigned long for a user count for like number of users, something like that, okay? At some point in time, you will have to initialize this structure and then prepare it to go ahead and be sent over to your C2 infrastructure. Okay, so how in the world can we initialize a structure like this with brace initialization? So there are a number of different ways that you can do this. The very first method, where I say message thing, and then we have the empty braces. By default, that is going to initialize every single field in that structure to 0. Okay, so it's implicitly already saying 0 initialize. You could go ahead and be explicit about that and just put the 0 in there anyway to enhance readability, but you really don't have to. Another option for thing 1 is you can use dot notation inside of the braces and say dot username and initialize that. And you can do like dot user account and initialize that with 670. And then also another option is for thing 2, if you know the order of the fields of the structure, you can go ahead and use the order to go ahead and initialize things like hello and 670. And also for strings, we have standard string and standard W string down there at the bottom, using brace initialization for initializing those strings. I do want to call out the L, the capital L, right before kernel 32. That is our indication of a W string, UTF-16, or as Windows likes to use, Unicode throughout. Moving over to standard vector. What we use in our custom loader in a class is we use a standard vector that is just a vector of bytes. So we'll go ahead and we will receive raw bytes of the DLL, either in the form of a GET request or POST request or coming from a socket or something like that. And then we'll store those raw bytes of the DLL in memory. Then we have to go through later and start to parse and make sense of those raw bytes and kind of like, if you will, transform that into an actual PE image, like make it make sense, okay? With a vector, they have a method called the .data method. Many containers and methods in C++ have this .data method that you can call, which will allow you to go ahead and access the underlying pointer to this particular object. Other things we have is .begin, .end, kind of what's in the name. I think that's kind of self-explanatory there. Begin, the beginning of the vector, the end is the end. And then we have .empty. .empty doesn't actually empty out the vector. Rather, it will tell you if it's empty or not. So if you want to do a simple check to say, hey, do I even have anything here inside this vector? Yes or no. Then you can go ahead and take whatever code path you need to based on how that returns. If you need to add anything to your vector, there is a pushback method that you can call to go ahead and say, let's go ahead and basically append, if you will, some data to your vector. Moving over for standard string, W string, I kind of showed this already with the brace initialization, but just calling it out on its own specific slide of how you could go ahead and create some strings inside your program. Now, OPSEC-wise, when you're creating some implants to be used for red team engagements or pen tests or whatever, you would not go around and just saying create tool help 32 snapshot or kernel 32. You want to either make a hash of the string or find some way to do some obfuscation. With C++ being super awesome, there are a lot of libraries out there that allow compile time obfuscation for strings, which is really, really, really awesome to have. Then we have decal type. Decal type is kind of cool in the sense that is a way to basically go out into a variable or some kind of object and return to you the type of that object. So for example, if you have the variable, let's just say int class equals some kind of value, right? So we know the type is an int, right? So decal type, you can go ahead and say decal type class, and it'll go out there and say, okay, what is the type for the class variable? Oh, okay, it's int. I'll go ahead and return int to you, and you can create another variable that way. But how we can use that inside of an implant is to go ahead and say, I'm going to give you the name of a Win32 API, like Internet Open W, all right, for the wide character or the Unicode version of that API, and say, I want you to go ahead and find the type for this API, return that back, and create a function pointer around that particular function. Okay, so we can do this several times over and fill out a structure like this one for the WinInet table. I like using this inside of my custom loaders. You can think of it as your own custom import address table, if you will. So you can have one for WinInet, the WinInet library, kernel 32, kernel base, so on and so forth. You can have these filled with function pointers for that particular library. All right, and then we have standard bitcast. Okay, so this is definitely very modern in C++. And with bitcast, now you can go ahead and kick aside reinterpret cast. How many of you have used reinterpret cast? Just a couple, one brave soul to raise their hand. So yeah, so reinterpret cast, right? It's cool. It was awesome for what it was. It can introduce some undefined behavior, but now we have bitcast, which is basically a very fancy mem copy that introduces type safety. All right, so how in the world can we use standard bitcast inside of an implant? All right, so we can do a combination using decal type and bitcast all at the same time. So we'll say decal type, close handle, okay, so dealing with like a function pointer. And then we make a call to a custom routine, which is basically our own implementation of get proc address. So go out to some DLL, find out where close handle is actually being exported, take that address, use decal type to kind of cast that for the type for close handle, and then bitcast. All right, so go ahead and grab the underlying bits that are there that represent this object and kind of copy them over into a different variable or a new variable. Okay, now go ahead and kick it over to Kevin.
All right, thanks. So now that we got a glimpse of some of the more modern features of C++, let's see how we can actually put that into practice. And for this, we chose to demonstrate from the 670 class one of the labs, which is creating a loader to manually map a DLL. So for those that have done a bit of red team tool development or so, are probably familiar with reflective DLL injection, where the DLL is just put into memory, and then a reflective loader is appended to the DLL and does a lot of the bootstrapping of the DLL itself in memory. Now, with manual mapping, we do everything from our loader process instead of having like a lot of small bootstrap code that will do the DLL mapping in memory. So to understand DLL mapping in a nutshell, so there's a lot more to it. This is a bit simplified, but just to give you a quick overview of what needs to be done. So as John already said, we need to have the raw bytes. So in the case of our lab in 670, we just load the bytes from memory. But you could also receive the bytes from an internet endpoint or a socket, and then try to load these bytes. So first, we need to get these bytes into memory. We can see here the typical MZ header of our DLL. Once we have those into memory, now in a portable executable, all the sections that are in the executable have a virtual address. So we cannot just leave it in memory like this, but instead we need to copy the individual header and sections into memory. For that, and this is also part of a more like proof of concept style, we just allocate one large section. We reserve the memory as read-write executable, just to simplify it a little bit. And then we start copying over the individual sections and the PE headers in their right location in memory. Once we have that, we need to do what's called relocations, because every DLL has a so-called image base or preferred image base, which it wants to be loaded. And a lot of hard-coded values, so global variables or absolute jump instructions, they contain the hard-coded value of the destination, be it the global variable or destination of the jump. So if we are not able to manage to place our DLL on the preferred image base location, these absolute addresses will not work anymore because they are on the wrong offsets. So with relocations, we basically go over all the different sections and fix static or absolute addresses by switching them out with the correct ones based on the location where our DLL was loaded in memory. Once this is complete, one thing that the Windows loader normally does for us is resolving the imports and placing the correct addresses of functions, for example, from kernel32 DLL or user32 DLL in the correct locations in the import address table. As we don't have the Windows loader available to us now because we want to manually map our DLL, we need to resolve the import address table ourselves by parsing the import address table and then parsing the exports of, for example, kernel32 DLL and replacing the addresses in the import address table. Once we have fixed the relocations and our import address table, the last step is then to call our DLL entry point. So I omitted two steps, which is fixing TLS callbacks and function pointers for exception handling in 64-bit binaries. That's also something that goes a lot more in detail, and because we are a bit time restricted, I just decided to skip over this, but those are also steps that you can do, but you don't have to do, depending on the DLL that you're trying to load. So let's do a bit of code review in how we can use modern C++ paradigms to actually improve our loader code and make it a bit more type safe and memory safe for use, for example, in a C2 agent. Okay, so first of all, what we did is we are wrapping our loader into a class. And this is especially important for resource management. A lot of proof of concept code, a lot of code that you see on GitHub and online use just classic procedural programming where just one function after the other is called. Maybe there is at least a structure that tracks a few of the values that you need for the loader, but it's not very coherent and it's very hard to integrate into existing tooling. By using a class and encapsulating all the values that we need to track into our class, it makes it a lot easier to track certain things. For example, we can now track the different image allocations. We can now track the locations of our headers of the executable, the DLL in memory, and we can track our payload bytes. So for the methods that you see, we have, of course, the default constructor. So that just means that the constructor is doing basically nothing, and it just initializes the object, because we then use the load method to explicitly do the loading of our DLL bytes into memory, and then the call entry point to, after the class has been loaded, call the entry point and execute DLL main as we want to. And as you see, there are two different sections for private, and that's the main reason for that is to separate private variables, like members of the class, and private methods of the class, so that it's a bit better readable and a lot cleaner and easier to maintain in the long run, especially if you, for example, have other people coming in to help you with your code. They will appreciate if you separate out certain things and make the class more maintainable and more readable. And then in the private methods, we can see that we have exactly the steps that we need to do in order to load our DLL, replicated as class methods, which is to perform the relocations, resolve the imports, and copy the section table. So one thing that we can do with modern C++ is use smart pointers. So smart pointers basically manage the lifetime of a pointer. There are different versions of smart pointers, including unique pointers, shared pointers, and weak pointers. Unique pointers are exactly doing what their name implies. They hold a pointer and try to guarantee that there's only ever one copy of this pointer. So there's only ever one object holding this pointer, so that no one can try to take ownership of that pointer without or by making a copy. So that, for example, vulnerabilities like use after freeze or double freeze can be eliminated. We can use smart pointers because we're working in the end with pointers of to our loaded memory. We can use smart pointers to track the lifetime of our loaded DLL. We can use it to track allocations of the headers and of the individual sections. The problem is that because we are using virtual alloc in our loader, default smart pointers do not work with virtual alloc. They are supposed to work just with the new and delete keywords from C++, but not with Windows APIs. One of the reasons is that because the smart pointers take care of the lifetime of the object, they need to understand how to free what they're pointing, how to free the pointer that they're pointing to. And with virtual alloc, there's no normal free method, and you cannot use it with delete. So virtual unique pointers do not support virtual alloc. So what we need to do instead is we need to create a specialization of our unique pointer and provide a custom deleter. The custom deleter in this case can be a few different constructs within C++. They can either be lambdas, they can be an std function, or they could be a functor. For this case, I decided to use a functor, which is called virtual alloc deleter. And the definition of the functor is basically a struct that has an operated, an overwritten function call operator. So by overriding the function call operator, you are basically creating what's called a function object. So it's an object that behaves like a function. And this function object can then be used in the specialization of our unique pointer to create a unique virtual alloc pointer that can actually be used to track and automatically free allocations done using virtual alloc.
Stuff like that is really good to keep in mind as you're creating implants, just from the perspective of OPSEC. So for example, if you're trying to get some shellcode into a page of memory and shellcode executes or whatever, does this thing, it's done. Doesn't need to be there in memory anymore, right? Once it did its job and it's no longer needed, why let it sit in memory to possibly be detected at some point down the road? So some of the things you can think about when you're doing implant dev is to say, okay, what do I actually need to have staying resident in memory? So you can keep that in mind. And anything that you could go ahead and determine that you don't need in memory anymore, let's go ahead and clean up after ourselves and get that out. That way it can hopefully increase your dwell time on the box.
Yeah, 100%. So that's a very good use case, cleaning up after yourself and making sure that any malicious bytes that you put in memory are cleared up after you're done with the function. This is mostly not relevant in proof of concepts, but especially if you use something like this in a long-running C2 implant, then it is very important to keep track of the memory you're allocating and freeing that memory when you're done. The problem with unique pointers is that a lot of Windows APIs and other low-level C APIs do not support smart pointers because that is a C++ construct. So we have a solution for this, and we can basically use the get function of a unique pointer to retrieve the underlying pointer. This, I mean, it's a bit like the unsafe keyword in Rust. You're basically now accessing the underlying pointer. If you free the pointer by using get, you basically store a freed pointer in a unique pointer. So there's still a lot of, like the burden of correctness is still on the developer. It just gives you a lot of methods to try and implement it correctly. So this is an example. Here we are tracking our loaded headers for our portable executable. And we are using the reset function to store the pointer returned, the void pointer returned by virtual alloc in our smart pointer. In this case, we're using the reset function because it didn't write an override for the assignment operator, so the equal sign. You could do that. Then you could just do loaded headers equals and then the result. But if you don't override the assignment operator, then you can also use reset to free what's already there and place a new header in the place a new pointer inside of our unique pointer. And then, for example, in this case, we're using a function that has a not smart pointer compatible interface. And so we need to use the get function to retrieve the underlying pointer and pass that into the function. So now, how can we use these smart pointers to actually track things? So within our class, we do have a vector of smart pointers used to track each allocated section. So what we're doing is exactly what we did before. We use the reset method of our smart pointer to place the currently allocated section in our unique pointer. Then we do a bunch of stuff. In this case, we're copying the raw bytes from one location in memory to another location in memory. And once we're done with everything we did, we now want to keep track of that specific unique pointer. And that happens here. So we already saw that in the vector, you have the pushback method to add a new element to a vector. The problem is that we're facing now that unique pointer guarantees that there are no two copies of that unique pointer. And because the pushback normally invokes the copy operator, the copy constructor of an object, this doesn't work. So in this case, we need to use std_move, which will basically create a new unique pointer and then move ownership of the underlying pointer to that new object that will be placed in the vector. And by this, we can start then tracking the individual sections. And once we're done with our loader, the constructed objects will automatically take care of cleaning up our sections behind us. So the last concept that, I think the last concept that I want to introduce is abbreviated function declarations. So whoever has done a bit of coding under Windows, especially when it comes to portable executable or shellcode, probably has seen this macro, RVA to VA. So relative virtual address to virtual address. It's a macro, so that means there's literally no type safety. It's just a search and replace function that the compiler does. So if we want to use something that's more type safe, we could use a templated function. So for everybody that has done some C++ and fierce templates, it's not that bad, especially if you use it in easier or smaller functions like this. So by templating a function, we can also pass in arbitrary types and then cast these types to a uint pointer type, which is just an alias for an unsigned long. And we can then use that to add our offset to a base address and return that value to the caller. Now, we're talking about modern C++. This is C++ 11, so this has been around for a while. A cool thing that has been introduced in C++ 17 is auto for function parameters. So the auto keyword already existed for return types, so that the compiler could automatically derive the return type of a function. But now with C++ 17, we can actually do this and replace our template by just using the auto keyword for the function parameters. Now, the compiler will go ahead and basically convert this back into a template, but we can use another layer of abstraction to get, for us at least, rid of templates, because a lot of people dislike templates, and just use auto to still implement generic programming without the implicit or explicit use of templates. So we have the auto to automatically derive the return type of the function, as well as auto for both parameters to then automatically derive the types of the variables passed into it. Okay, so now that I've shown you a few of the concepts that you can use to simplify your loader, we actually wanted to give you a small demo to show how this would look like in an example.
Fingers crossed.
Fingers crossed. Yeah, let's pray to the demo gods that this actually works.
It worked.
So, as you can see, I have added a lot of output to this demo just so that you can see what actually happens. So first, it maps the headers. When you can see that it is not able to allocate memory at image base, that is forcefully introduced into the program just for this demo. Normally, it tries to map it at the image base. If it succeeds, it does not have to do any relocations, which save us a bit of effort to do in a live environment. But for this case, I wanted to show how it actually works with the relocations. And the next section that we can see is the individual, or the next output that we can see are the individual sections with their virtual addresses, and those are accordingly then copied into memory and saved into our vector of unique pointers. So then after the relocations are applied, and we resolve all the imports for kernel 32, because it's a very simple DLL that we load, we can then see that we just call the address of entry point. So this is for DLL, not the main function, but the DLL main function. And the DLL that we're calling is actually from the class as well. It's a small proof of concept on how to create a DLL, and it does nothing than just print hello DLL. So what this output shows us is that we're able to successfully load and invoke a DLL and its entry point. And we did it completely by mapping each individual sections, performing the relocations, and applying the correct imports in the import address table. So now the cool thing that we see after the DLL has been invoked is that it is now actually freeing all the memory that we had allocated for our DLL. So if we compare this, we can see that the address at which we reserved our memory is C000, and then the first section would be at hex 1000. And if you add those, this would be basically this address. So we can see that it frees each section as it has been allocated, one after the other. And I didn't have to write any code to do that freeing, because I had the unique pointers that I created before do the freeing for me. And then at the end, we can see that the reserved memory for the whole section where we copied our DLL into has been freed as well. So also within the lab in 670, we do a lot of enhancements, like not allocating one large sections of read-write executable memory, which is a huge indicator by itself, but instead allocating each section with its corresponding section protection as defined in the PE headers of the DLL, just as an example. Okay, so that was the demo. Thankfully, it all went well. And with that, I would kick it back to Jonathan to wrap it up.
Thanks. One thing I like to do when teaching and stuff and building out labs for the course, especially around a programming kind of course, is having some of those print statements as your code or as your lab is executing, because I want you all to have some kind of introspection into what's happening behind the scenes, and then having all those addresses and stuff being printed out as well. You can go ahead and validate that using WinDebug or WinDBG. It's a little bit more fun to say it that way. But it's a nice way to go ahead and say, is my loader actually doing what I want it to do? Validate some of that stuff in memory with the debugger. You could use x64debug or whatever you would like to go ahead and provide some of that validation for you. Once you have that validated, everything is working good the way you want it, go ahead and get rid of all those print statements. I mean, let's be real. Nobody is writing an implant that prints anything too standard out. I hope not. I hope not. If that's you, let's talk. Let's fix that. But yeah, so one of the other things that I always love is I love having like an interactive session. So if you have any questions, please feel free to ask. Be more than happy to chat about what we talked about the course, stuff like that. It's very, very, very heavy with labs. Probably like a 70-30 split, 70% lab time, 30% slides. Okay, so it's gonna be very, very heavy with labs and coding. So if you think you're gonna come in, you're just gonna cruise, sorry, it's not gonna happen. Okay. Just one little plug, self-promotion here. The course is running at CDI this December in Washington, D.C. So it'd be great if you're interested, come on and sign up for in-person, because we offer some extra fun things to do in the classroom. All right, that's all we got. Thank you so much.
Thank you so much.